It's my great honor to introduce our speaker today. Dr. Bhishek Manek is currently a postdoc research scientist at Laboratory for Atmospheric and Space Physics at CU Boulder. He earned his PhD degree at the end of last year at University of California, Santa Cruz, supervised by Professor Nick Brumell. And he has also been a Newkirk Research Fellow at High Altitude Observatory NCAR Boulder. His research interests include magnetohydrodynamics of the deep solar interior, flux emergence at the solar surface, and the theory of magnetic reconnection. He is also a member of the COFFIES Convection team. Let's thank to the speaker, and Bhishek, you can have your seminar.
You're muted.
Oh.
Bhishek, you're still muted.
You're still muted, Bhishek.
Yeah, okay. Hi, everyone. Thanks, Rizu, for the introduction and inviting me. I'll be talking about rise of magnetic flux tubes through convection in this talk. Right off the bat, what we see in this slide is a couple of figures. First one is sort of a toy figure explain we have, and the top one explains the major features that we have in our simulations. So we'll be talking about convection. We'll be talking about a two-layer setup where we have convection like this and a radiative zone. We'll be talking about large-scale background magnetic fields and a flux tube. So these are the primary things that will be coming along quite often. And this work was like part of my PhD thesis, which I did with Nick Brumell. This work was also done by Christina Pontin. So some outline. I'll give a brief overview of solar observations. Basically, what motivates us to treat magnetic fields in the solar in solar physics as flux tubes. Some background on previous studies that have been done on magnetic flux tubes, recent observations of relatively recent observations of magnetic and current helicity, and then talk about some model results and conclusions that I have. So many of you might have seen these slides if you attended my previous talks, but for the sake of completion, we go through them again. We have solar observations. So what we see over here is sunspots embedded in an active region. If we look at them closely, what we see, I mean, from this chart figure is basically magnetic field lines poking in and out of solar surface. Now, this sort of a observation basically motivates the idea that magnetic fields might be emerging from below the solar surface in cylinder-like structures. Now, to magnet on the interior of these as cylindrical. The important mechanism, which is basically the important mechanism which governs how these magnetic fields rise through the interior of the surface to the solar surface, is basically magnetic buoyancy. Now, the concept behind magnetic buoyancy is quite simple. It's basically if you have a magnetic flux structure embedded in a background stratification, you'd have inside the flux structure some gas pressure and some extra magnetic pressure. Now, if you assume some basic standard things like there's pressure balance between the magnetic flux structure and the background stratification, and then there's temperature balance. If you assume that, what we basically get is that the density inside the magnetic flux structure would be lower than the outside stratification density. So it's basically magnetic fields over here would be lighter and they'd start rising. So that's the basic principle which drives the transport of magnetic fields from the interior to the outer surface of the sun. This concept was given by Parker in 1955. to give you a brief introduction of what all has been studied in magnetic flux tubes, using magnetic flux tubes, there's quite a broad range of simulations, theoretical work that has been done. We can broadly divide them into two different parts. First one is basically where you treat your magnetic flux tubes as isolated structures rising through a stratification. So this stratification doesn't have any magnetic fields, and the flux tube basically rises through it because of magnetic buoyancy. The other broad range of studies that has been done is basically flux instability studies. Now, here you know that flux tube is to start used to scale flux sheets which go unstable and then form these tube-like structures, which then would rise due to magnetic buoyancy. An important point to note from these earlier works that we have found is that when you have these tube-like structures forming, they need to have some non-axial field or twist to maintain their coherency as they are rising through the turbulent solar interior. The flux sheet instability studies, they can be subclassified where you actually study the formation of the sheet too, and don't assume that there's a sheet already present. Primarily, this is about what we know as where you have these magnetic field and the velocity on it to form a scale.
Can I interrupt real quick?
Scale horizontal field. Yeah.
Your sound is breaking up a little bit. Do you have a good connection?
Yeah, I think so. Yeah, I mean, if it happens again, I'll try to change the connection. But this is the most stable one that I have for now. So over here, basically Brummel, Klein, and Wassel, they studied in early 2000 is that if you have a large scale vertical field with a velocity differential applied to that, you'd see that there's a large scale sheet forming, and then the sheet can go unstable, forming again cylinder-like structures, which may be buoyant and rise through because of magnetic buoyancy. An important point to note over here, which is critical to the work that I'll be discussing, is that these cylinder-like structures which are forming, they are not magnetically isolated. They are present in a large-scale background field. So there's a large-scale magnetic field through which they have to rise. That's one of the primary motivations of this work, that you cannot treat these cylinder tube-like structures as isolated. Now we can look at these simulations of Manek and other authors closely. What we see over here is field lines of the axial field. Now over here you have, I mean, one thing which is right away clear is that the field, this basically formation of tubes, and is that these flux tubes are inherited when they are. The second figure over here,
a little bit.
which sorry, let me give this a try. I'm not sure it works.
You can also try, as much as we love seeing your beautiful face, if you try turning off your video, the audio might work. Did we lose him completely?
Can you hear me now?
Yeah.
Yep.
Okay. Sorry. I'll just repeat this one. So over here we can look at the study, these flux sheet instability studies, where you actually study the formation of flux sheet 2 in detail. In this figure A, what we are looking at is magnetic field lines of the axial field. And what we see is that when you have these tube-like structures forming, they are inherently twisted. So these field lines have some field line twist over here. The figure B shows these axial fields as volume rendering overlaid with the large scale horizontal field. And it's very clear that you have these flux tubes, tube-like structures, which are embedded in a large scale horizontal field. Now, taking a step back and looking at some of the relatively recent observations, there are observations of magnetic and current helicity. For this particular talk, we'll be focusing on current helicity. Very vaguely, what helicity, vaguely what helicity sort of means is that it's basically a measure of the twist and right of magnetic fields. So it basically quantifies how complex your magnetic fields are. Now, current helicity is basically defined as volume integral of P dot J. This quantity has some magnitude and a sign. We'll be focusing on the sign quite a lot. So what do the observations of helicity tell us? Now we look at this latitude time plot over here. We have this butterfly diagram, which we have seen quite a few times. Now, the open circles, they denote negative helicity signs of active regions. The filled circles, the open circles denote positive helicity of the active regions. The filled circles denote negative helicity of active regions. Now, if we focus at solar cycle 22, what we see is that there's negative helicity active regions are predominant in the northern hemisphere, and positive helicity active regions are predominant in the southern hemisphere. If we go from one solar cycle to another solar cycle, so over here from solar cycle 22 to 23, we see that the trend remains the same. So we still have negative helicity active regions more appearing in the northern hemisphere as compared to positive helicity regions in the southern hemisphere. So it's not so much as a rule, but it's a trend of helicity preference in particular hemispheres from one solar cycle to another solar cycle. It's a weak rule. This is followed for about 60 to 80% of active regions. Interestingly, it doesn't change sign when you move from one solar cycle to another solar cycle. Now, the model setup that we have. So we are solving compressible resistive MHD equations with fluid viscosity and thermal conductivity. I'm using HPS code written by Nick over here. So we have basically the equations of mass conservation, momentum equation, temperature or the energy balance, magnetic induction equation with solenoidal condition. Some of the interesting and important parameters which we have in this study, one of them is Q, which is the Chandrasekhar number. Now over here, there's some parameter alpha, which is basically a multiplication of these things, which are basically Prandtl number, Schmidt number, and the thermal dissipation parameter. This one is an important parameter. If we assume that the Prandtl number and the Schmidt number and the other thermal dissipation parameter is constant, this alpha is basically directly proportional to Q. Now, this alpha comes in front of the Lorentz force. So in a very vague way, Q basically determines how strong your imposed magnetic field would be in the simulations. So it also, in a way, determines how buoyant your magnetic fields are going to be. The background stratification that we have is also important to understand. It's basically a two-layer setup. So we have a convection zone with a radiative zone. Both the layers are defined by volutropes. Now there's a parameter called stiffness parameter, which gets introduced because we have a two-layer system. What the stiffness parameter tells us is how stiff your stable region is. In simple terms, what it would determine is when you have these convective motions in the layer 1, if you have a stiffer, if you have a stiffer or the S parameter is larger, it would mean that the convective motions couldn't penetrate easily into layer 2. So larger the value of S, it's harder to penetrate the stable region. So over here, I show basically temperature and density profiles for 3 different values of the stiffness parameter. Yeah. So I mean, to basically, yeah, is there a question? Okay, to set up the initial condition that we have, like a flux tube with convection zone and a large scale background field through which it has to rise, we have to take a number of preliminary steps. So we start with overshooting convection, basically set up a overshooting convection setup, and then determine if a flux tube is buoyant enough to rise through that overshooting convection. That's going to be our step 2. And then we set up a background layer self-consistently, and then study the full problem that we want to study. Basically, flux tube rising through a large scale background field and convection. Now, to start with overshooting convection. So we start with purely hydrodynamic calculation with some random noise. What we see over here in this figure is vertical velocity. So basically red is hot, rising up, blue is cold, rising down. So we have these downward plumes followed by some upward motions. It initially starts with a laminar sort of flow, which quickly gets turbulent. So over here we see various down plumes and the up plumes over here. We have some parameters determined for this. So we have Rayleigh number 4×4, Prandtl number is 0.1, the stiffness parameter is 7 over here, which we, unless otherwise stated, we'll consider these as standard sort of parameters that we'll use throughout the stop. Once the turbulent convection sort of reaches a steady state, we take this overshooting convection setup and introduce a flux tube. Now this is very important because we want to determine whether a flux tube is buoyant enough to actually rise through this convection. Once we know that, we can introduce the large scale background field. So this figure is basically a composite figure. The red-blue color scale shows the vertical velocity over here. The green color scale over here shows the axial field. So it's basically the field going inwards. And it's plotted at 4 different times over here. There's some G parameter ascribed for this particular setup, which is 2×10⁸, basically controls the buoyancy of this magnetic flux tube. Now, over here, what we see is that the flux tube starts rising, forming vortices. Eventually, there's an effect of convection, but the flux tube still is able to rise to the top of the simulation domain that we have quite coherently. Now, an important point to note is that Q controls the buoyancy. So how does the dynamics change when we change Q? So over here in the simulation, keeping all the other parameters constant, we decrease the value of Q. So if you introduce a flux tube in the stable region and it's buoyant because there's magnetic field over there, starts rising. But as Q is lower, so basically the buoyancy is quite weak. The flux tube doesn't successfully rise through. So we are not interested in the cases over here which do not rise through even just with turbulent convection present. So we can carry out a broad range of studies which we did. So you vary the value of Q, which controls the buoyancy of the flux tube, from weak values like 5×10⁶ to quite stronger 2×10⁸. The figure over here shows what the maximum of axial field is. So it's basically trying to track the flux tube as it rises through the simulation domain. So it's a Z coordinate plot with time. Now what we see over here is that if you have the Q values to be sufficiently strong, so the flux tube is buoyant enough, the flux tube rises quite quickly through the simulation domain. For weaker values, the flux tube doesn't rise through and remains in the stable region, sort of eventually getting destroyed. Now, once we know some values of Q for which the flux tube is successfully rising, now we want to study a setup where the flux tube isn't isolated, but it's rising through a large scale background field. Now, to arrive at this large scale background field, we self-consistently develop this background field. So we start with a setup where there's convection present. What this figure shows is just the horizontal field. So we impose a layer of horizontal field over here in the presence of convection, and we study its evolution. What you see right away is basically a competition between two mechanisms. First one is magnetic buoyancy. So there's a magnetic layer. So the buoyancy forces would try to take the magnetic layer upwards, but there's also convective motions, turbulent convective motions, which try to push the magnetic field downwards. Now, if we evolve this simulation for quite some time, what we notice over here, I'll just try to skip and take this simulation forward. What we'll see is that eventually over time, the turbulent pumping due to convective motions sort of dominates over magnetic buoyancy and creates a large scale horizontal layer consistently. Sorry, are there any questions? Can you hear me properly?
I have a question. It's Shay over here. Our sound system's a little funky. So this isn't my area of expertise. Is there a physical explanation of what Q is? I'm trying to wrap my head around that. I know you said it's like the amount of buoyancy or like level of buoyancy, but what does that mean?
I mean, it's in some ways the strength of the magnetic field that we are imposing. So the flux tube strength is in some ways determined by this Q value. So if you have larger Q value, that's basically your flux tube having more magnetic field as compared to if you have lower Q value, flux tube isn't that strong.
Okay, thanks.
Yeah, so I mean,
Sorry, one more question. You may have mentioned this. What are the spatial dimensions here? Is that megameters or?
Oh, so these are like non-dimensional complete simulations. So yeah, I'm not sure what the conversion over here is, but we have, I mean, the idea basically was to have a horizontal domain, which is quite large as compared to the vertical domain. So over here, the convection zone is of size 1, whereas the horizontal spatial scale is of 6. So that's an aspect ratio of 6:1 for the convection zone.
Good, thanks.
Yeah, so what we have over here is basically a large scale horizontal field, which got self-consistently generated because of these competing magnetic buoyancy and turbulent convection acting on it. Now we'll be using this in the next studies, but we can look at this sort of movie in a different perspective. We can divide this long movie in 4 different parts, which we have done over here. What the figure shows is the horizontal average of horizontal magnetic fields on the x-axis, whereas the depth on the y-axis. Now, the initial fields over here, the initial and the final fields are shown by these solid curves. This isn't a very great figure, but we start with this initial field over here. Some of it starts going up because buoyancy, some of it starts getting pumped downwards because of turbulent convection. Now, if we look at it over time, there's some sort of vacuuming going on where the magnetic fields in the convection zone over time starts getting reduced, and they start getting accumulated either at the top over here, a fraction of it, or towards the bottom of the convection zone. Now, if we evolve this simulation for quite long, eventually we see that the magnetic fields in the convection zone have completely sort of vacuumed out, and we have a sort of a layer generated at the bottom of the convection zone. So once we have this layer, we take an average of this layer. So it's an average over time. The background layer looks something like this. The x-axis again is the average of horizontal fields plotted as a function of depth over here on the y-axis. These sort of diamonds which I have put, they basically represent what the strength of this pumped field is at different locations. So over here we have a 20%, 20% relatively speaking strength of the horizontal pumped field as compared to 1% over here. So there's a range of values that we'd be considering. Yeah. So now we look at the major question that we were going to address. Basically, flux tubes rising through a large scale background field. So they are not isolated and they are rising through a convection zone. Now what we have in these figures is like, so at the top we have a positively twisted flux tube. At the bottom we have a negatively twisted flux tube. The figures on the left show the horizontal sort of magnetic field. So this one gives an idea that we are putting a flux tube over here, which is sort of twisted. So there's some non-axial magnetic fields along with this large scale layer of background field. Over here, we have the axial field. So that's basically the field pointing inwards. Now, what we see over here is the flux tube is placed on top of this pumped background field such that the flux tube strength compared to the background field strength, the background field strength compared to the flux tube strength is about 0.10 or 10%. Now, over here, we see that in the top case, when you have a positively twisted flux tube, the flux tube sort of rises. There's some effect of the background field. There's flux loss along the background field. But even then, the flux tube still rises as a sort of a coherent structure. But when you have a negatively twisted flux tube, what you would see is that the flux tube doesn't rise at all. Even though it was magnetically buoyant, all the other parameters were same. Q was 210⁸, which we determined was good enough for the flux tube to rise through this convection. But just the presence of background field created some hurdles for this flux tube to actually rise through coherently. So that's one major result that we have right over here. If you have a flux tube differently twisted, it behaves differently when it rises through a large scale background field in the presence of convection. So we'll come to the reasons of this in some time and also what implications it has. But we can do a larger, broader survey over here. Again, what we are plotting is sort of a quantitative measure of the plots that I showed you before. We are plotting the Z location of the maximum of the axial field. So it's basically the y-axis is basically tracking the flux tube as it rises through the convection zone as a function of time. The figure A over here shows the cases with positively twisted flux tubes, and the B figure shows with negatively twisted flux tubes. Now, the different colors show the different locations of the flux tube where we basically place the flux tube on top of this background field. So depending on where we are putting the flux tube, the strength of the background field that the flux tube experiences initially changes. So we change it from relatively low, so 0.01, to relatively stronger, 0.20. So basically from 1% to 20%. Now, interestingly, what we notice is that for positively twisted flux tubes, most of the cases, the flux tube rises. So like for up to like 15% background field strength, the flux tube rises quite quickly and reaches the top of the simulation domain. If you go beyond 15%, the rise of flux tube is difficult and it doesn't seem to rise. These are discrete simulations, so there's some error over here, but even with that, we'll see the stark difference between these two different cases. So when we look at negatively twisted flux tube, what we see over here is that the flux tube rises relatively slowly as compared to the positively twisted flux tube, but it still rises nonetheless for 1% case, 2.5% case, and for 5% case. But if you increase your background field, so basically you are putting the flux tube sort of deeper into the pumped layer that we had, the rise becomes quite difficult and we don't see any coherent flux tube rise. So anything beyond 5% is quite difficult to rise. So again, this shows the major result that there's a stark difference between how a positively twisted flux tube behaves, the dynamics behave as compared to a negatively twisted flux tube when they are rising through a large scale background field. Note that if there was no background field, both of these cases wouldn't know the difference and they'd rise similarly. So there's two major questions over here. I mean, one could argue that it might depend on how the pumped field how we arrived at our pumped field. So we took an average over time. Now, depending on what time you take the average, the overall background field could be varying with time because there's still convective motions going on. So that's one particular sort of a source of uncertainty, which we could say. And then also, it also depends on the horizontal location where we put the flux tube. So the average field, background field might be the same, but if we look at the spatial location of the flux tube, the local background field that the flux tube experiences while rising, it might change. So that's two major sources of uncertainty that might arise in these simulations. So we try to address those. So the first one is effect of initial conditions. The A figures say that T equals to T1. That basically means that we have taken the average of the pumped background field over a certain period of time. The figure B shows T equals to T3. That's basically saying that the average was taken over a different period of time, so that we have some mixture of different initial conditions. Now, again, Q positive, that shows that the twist is positive of the flux tube. Q negative shows the twist is negative. We also vary the horizontal location. So XC is basically where the flux tube is placed in the horizontal location. So we could vary the location from 1 to 5 and see the difference. The figure again shows, I mean, it's basically tracking the Z location of the flux tube. So over here we have what we see, like if you look at figure A, we see that for a positive flux tube, no matter the initial location of the flux tube, it rises in all the cases. The rise is different because the sort of local magnetic field that it experiences would be different, but it still rises nonetheless. Now, if you have basically the same setup with negatively twisted flux tubes, the rise is quite different. There's no rise actually. Again, if we look at the average of background field over a different time scale, again we see that for positively twisted flux tube, most of the cases rise, but yes, there's some uncertainty, right? I mean, if you have the local conditions quite different, some of the cases might not rise, which we see over here that one of the cases doesn't rise. But for negatively twisted flux tube, none of the cases rose over here. So, I mean, even with these conditions changing, because there's turbulent convection present, there's these simulations are dynamic in nature, we can still say overwhelmingly that positively twisted flux tubes in the current setup were preferred to rise as compared to negatively twisted flux tube. Now, we look at another sort of variation, and then we'll discuss why this happens and what significance it has. We look at variation with S. S, as I said before, was the stiffness parameter. So it basically tells you how stable sort of the radiative zone is to convective motions, to penetrative convective motions. If you have low value of S, so the convective motions sort of penetrate quite deeper. The figure over here shows the horizontal field, like the pumped field that we arrive at after turbulent pumping happens. Now we can see there's significant horizontal variation in the pumped field. The pumped field is formed quite deep in the radiative zone because the stiffness is low and the convective motions can penetrate quite deep. If you have stronger, relatively larger values of S, the stiffness is large, the convective motions are quite difficult, find it quite difficult to penetrate in the stable region, and the layer is sort of more, in a way, streamlined and forms at a relatively higher location in the radiative zone. So this figure again shows like the average kinetic energy that we have from the purely thermodynamic, purely hydrodynamic calculations. And we can see that if you have S equals to 3, so lower stiffness, the convective motions penetrate quite deep. If you have S equals to 15, the convective motions don't penetrate as deep. So we study again the same thing. We have two different scenarios now, one with a lower stiffness and one with a higher stiffness. We arrive at some background field and then we start putting in flux tubes over here. So we have positive flux tubes, negative flux tubes put at different locations to vary the horizontal variation too. Now in this case, interesting things happen. Even though it's a positive flux tube, a positively twisted flux tube, in the presence of background field and convection, we see that some of the cases don't rise at all. Some of them rise, some of them start rising, but then encounter some sort of convective motion, which I know because I looked at some of these simulations in detail. This flux tube starts rising, encounters some strong convective downflow, and starts going downwards again. Now over here, for negatively twisted flux tubes, the results are quite clear. None of the cases led to any sort of coherent structure rising. Now, if you have the S equals to 15 case, so more stiff case, the background field is more streamlined. In this case, we see that basically all the cases rose. Some of them were slower to rise, but most of the cases rose through the convection zone and appeared to reach the top of the simulation domain. If you had negatively twisted flux tubes, none of them rose again. So again, there are significant variations when you have S equals to 3. So the stable region is sort of more prone to stronger convective motions, and there's significant fluctuations in the pumped background field that you have. Depending on where you put the flux tube, it can lead to some differences in the rise. But again, very broadly speaking, predominantly one flux tube twist was preferred compared to the other one. Now we come eventually, like we have seen some of the simulation results, what's actually happening. Now we look at it more clearly, like what actually is going on in terms of the physics of it. So what we see is that there's some sort of a selection mechanism at work, which is preferring one sort of flux tube, one sort of twist of flux tube to rise more preferentially as compared to others. Now, from all these simulations result, what we have is there's a background field over here, which is oriented in a certain direction. And then there's a flux tube, which has axial field PZ and some twist parameterized by the value Q. Now, Q negative is basically the negatively twisted flux tube over here, what we see in this case, we don't see a preferential rise from our simulations. In this case, we have Q positive. What we see in this case is a preferential rise. So this is from the simulations, what I'm showing over here as sort of these toy figures. The general rule that we can come to using these simulation results is that if you have the flux tube twist getting enhanced at the bottom of the flux tube, so there's some sort of a non-axial field, you have a background field oriented horizontally. If the background field works in such a way that it supplements the strength of the axial field at the bottom of the flux tube, we see more favorable rise. If the twist or the non-axial field gets enhanced at the top of the flux tube due to the presence of background field, we see less favorable rise. We can look at it in terms of forces acting on the flux tube. We can look at magnetic buoyancy forces, tension forces. Tension forces are sort of important, so I'll focus on those ones. What we see in this figure is tension force through a line cut at initial conditions. So over here, we are calculating the vertical tension force. So basically B dot del B for the vertical component. So this BZ should be outside this bracket over here. Sorry for that. We are looking at a zoomed in version. So these depth over here, it goes only from 1.4 to about 1.8. The dashed line is when there's no background field present. So you just have a flux tube. Doesn't matter whether it's positively or negatively twisted. The tension force is symmetric across this vertical line, and the net tension force would be 0. But as soon as you introduce a twisted flux tube and a background field is present, something interesting happens. I mean, over here, when you look at this positive twisted case, you'd see that the tension force sort of gets enhanced at the bottom, which I show over here as a cartoon figure. So the tension force getting enhanced at the bottom when you have a positively twisted flux tube and the background field is present. So the background field would always try to keep the flux tube sort of downwards over here. But when it's present in such a way that it supplements the twist at the bottom, it gives an upward net tension force, which pushes the flux tube to rise upwards. If you have a negatively twisted flux tube, the twist is getting enhanced at the top, and the net tension force is sort of downwards. So it tries to keep the flux tube from rising. That's the primary reason that we find on why such a differential behavior of flux tube, and why we come across such a differential behavior of flux tube when it's of one twist compared to the other twist. Now, an interesting question is like, what does this sort of signify in real solar sense? We can relate our simulations to some of the observations of helicity that I discussed. Now, what I'm showing over here is sort of cartoon models of what our simulations are doing. So the idea is that you have these large scale toroidal fields. There's differential rotation acting, which forms the toroidal fields over here, denoted by these blue arrows. The polyidal field is from red color. Now what we see over here is a flux tube forming in the northern and the southern hemisphere. It has certain direction of axial field, and the background field, which was the polyidal field over here, is present, through which the flux tube has to rise. Now, based on the selection mechanism that we arrived at, what we could try to figure out is what sort of twist of this flux tube would actually be preferred to rise. So over here, we have a certain orientation of background field. Now, if the background field, if the twist is such that it gets enhanced at the bottom, then it's more preferred to rise. Similarly for the southern hemisphere case. So we could see that if the flux tube is such that the twist is anti-clockwise, it gets enhanced at the bottom and it would start rising. Now, we could also analogously calculate what the helicity sign of this flux tube would be. That's simple to do because the helicity is basically B dot curl of B. So we want to use the right hand thumb rule. So if you take the curl of B for this flux tube, that's basically just, in a way, the curl is pointing outwards, dotted with the axial field, which is the blue colored field over here. They are in opposite direction. So curl of B dot B is opposite. So we have negative helicity of this particular flux tube. Similarly, we can do the curl over here. We have the, again, curl of B pointing outwards, dotted with the axial field. It's positive. So we have positive helicity in the southern hemisphere, which is preferred to rise. Now, this is exactly what we saw from solar observations too of solar hemispheric helicity. This was for one particular half of solar cycle. We could go at the other half of solar cycle. What basically changes in the other half of solar cycle is that the polarity fields change their sign. So rather than north-south, they are south-north now. The differential rotation acts in the same way, but because the polarity fields change sign, the toroidal field or the axial field in this case changes sign in both the northern and the southern hemisphere. We can again do the same right hand thumb rule, arrive at the signs of helicity, and it again shows that the preferred rise over here would be of negative helicity tubes from the simulations and positive helicity tubes in the southern hemisphere from the simulations, which is exactly what the observations tell us too. So, I mean, very broadly speaking, we have proposed a new mechanism based on rising flux tubes through a background field in the presence of convection, which are new features in our simulations that also explains various features of the solar hemispheric helicity observations. So basically that there's a preferred rise. There's also from no variation, like the preferential rise remains the same from one solar cycle to another solar cycle. And the dynamics are basically dictated by the magnetic tension force, or in other words, I can put it as what the relative orientation of the background field and the flux tube twist is. So we have some remarkable agreement with various features of solar hemispheric helicity rule. An interesting aspect of these simulations, which I didn't discuss, was that you can actually look at different simulations and try to find the causes of violations. As I said, this hemispheric helicity rule is sort of a preference. So it's followed for 60 to 80% cases, but from these simulations, we can actually pinpoint and find out cases which don't lead to this rise. So basically violations to the helicity rule, and try to investigate their causes, which we have done, and sort of a separate for some other time. We have some 3D simulations that we have been working at, but this is still some work in progress. So in conclusion, we proposed one sort of a unique way to club together simulations with observations of helicity. We are dealing with flux tubes, and we did one primary thing. We didn't consider our flux tubes as isolated. They were basically present in a large scale background field, and that made a whole lot of difference and led to these sort of interesting results, which could be correlated to solar observations. Not to say that this is the only and the primary theory which explains solar hemispheric helicity observations. There are other theories which take into account flux tubes rising through turbulent convection zone. And as they rise, they acquire some sort of a right, which is basically this sort of a kink of the flux tube. And as the helicity should be conserved, an opposite twist sort of gets developed, and that twist and that helicity is commensurate with the helicity observation. So this is known as the sigma effect. It was proposed by Longcoat et al. There are positives and negatives of both the theories over here. What we believe is that couldn't be just one theory that explains all. It might be in a more likely scenario, it might be a combination of these theories that actually results in the helicity observations that we see. Yeah, that's it. Thank you.
Questions?
I have one question concerning the initial placement of your flux tube. So I was wondering, yeah, just if you looked at placing the flux tubes at different heights, and yeah, if that changed anything about the selection or the simulation in general.
Sorry, can you repeat? I couldn't hear the last part.
Yeah, the last part was just essentially how the simulation is influenced if you place the flux tube different heights. Yeah, so I mean, if you place the flux tube at different height, it experiences different strength of the background field. And that background field strength basically determines if the flux tube would rise or not rise in this particular case. So if you have a flux tube rising through a strong background field, it's less likely to rise as compared to a flux tube which is placed sort of towards the top where the background field strength is weak. So this was somewhat over here in this one sort of clubbed figure. The different colors show different locations of the flux tube. So 0.01 means that it's placed somewhat at the top of this pumped field. If you place it downwards, then it's placed at some stronger field, in the presence of stronger fields. Does that answer the question? Yeah, so it seems like it doesn't matter that much where it's placed.
I mean, I would think if you placed it really close to the top, you would have much more of a chance of it actually rising. But, but in terms of like where we actually think they're coming from, I guess, like
that's part of the deal is that you would expect these tubes to form at the top of that layer. So it makes sense to look at it on the upside of that layer. If you arbitrarily, in these calculations, we're not forming the tube, so you can place them wherever you want. If you put them below the layer, then the integrated amount of field that it has to rise through is much higher, and that makes it much more difficult for it to transit. So there's two things to bear in mind there. Yes, you know, the deeper down, the harder it'll be for it to rise, but then we don't actually expect them deeper down. Yeah, so yeah, in terms of simulations, we tried out placing flux tube quite deep down, but none of these cases actually rose. So positive or negative twisted flux tube, they behaved in the same way, in the sense that none of them rose. So they don't lead to anything interesting to actually report over there. But yeah, it's sort of in question, which is open about where the flux tubes actually get formed.
Not a result important enough for the dissertation.
Sorry?
It was not a result interesting enough for the dissertation?
No, I mean, first of all, they are more likely to form where the gradient over here. I think there's some theoretical basis to it, which I'm not really sure at this moment, but the gradient over here is such that it prefers the formation of the flux tubes in this location. But if you put it below, none of these flux tubes rise, so they don't lead to any observable flux structure rising at the top of the simulation domain. So it's basically everything going to zero.
No, I mean, just to answer what Shay was saying is, you know, we're trying to correlate something with the, you know, solar hemispheric helicity rules, which is emergent tubes. So, you know, the thing we have to figure out is what is the mechanism which alters things which emerge. So if things don't emerge, in some sense, we're not interested in them.
Yeah, fair enough. Sushant, you asked a couple questions in chat. Do you want to?
Yeah. First, the profile of the tension force that you were showing relative to the location of the flux tube, which was in Z, which is depth, I think.
Yeah.
Do you expect the same profile in the latitudinal direction as well?
Yeah. In a very short way, yes. Also, I mean, it depends. Like if you are placing the flux tube in different locations latitudinally, so this was placed at a certain location x equals to 0, so the center of this horizontal domain, and we saw such a profile. But if we move the flux tube to x equals to 1 or something, and then we plot a similar plot, it would be basically same, but without having any flux tube. So I mean, the simulation domain is quite wide. If the flux tube isn't present, it would be sort of symmetric, which is, I mean, if there's just background field, then it would have some sort of tension, but it won't be something like this.
And the second was just a curiosity. If a flux tube which does not have the kind of helicity that is favored, if that kind of flux tube, the opposite helicity flux tube emerges, is it affected differently by the Coriolis force? Could it create like anti-Hale regions or something?
Yeah, so that's something which we haven't investigated, but that's an interesting question because currently we do not have rotation in our setup. But I mean, I think I discussed this question with Hong over here too, who's part of the COFFIES team, whether you could actually get Hale or anti-Hale regions from the cases where they are not expected to rise, but they still rise, and the Coriolis force might act in such a way that they lead to actually anti-Hale regions. So I'm not really sure, but that's something which is open for investigation.
What do you mean by anti-Hale here? Do you mean that the twist is different or the ride is different?
It's actually the tilt that is different, and the leading polarity sign is opposite.
So you're talking about the ride of a tube, not the twist of a tube. These simulations only know about twists of tube. They don't know anything about it.
Okay.
Did you want to add anything to that, or?
Yeah.
No? Okay. Any other questions? I think Nick has been fielding at least a bunch of the ones that I've had in situ in chat. Does anybody else have questions that they'd like to ask? Yeah, Jermaine, go for it.
Yeah, I have a general question.
Mm-hmm.
So in this presentation, you most use the dimensionless units. So I'm wondering for typical
Sorry, your voice.
You're cutting out a little bit.
Does it take to rise from the decompression process? And if you can give us some estimates of how long it takes for a typical flux tube to rise from the convection zone to the surface, because in the simulation you only gave dimensionless units.
Yeah, so I mean, I missed out a part of the question towards the start of what you asked because of the voice. But I mean, from what I understand, we are dealing with non-dimensional units over here, so I do not have a solid grasp of what actual timescales the flux tubes sort of rise through the realistic convection zone in terms of like seconds, minutes, or hours. But what we found is that they're sort of differential, and that was the primary thing. Can you repeat, sorry, the last part of the question? I think I zoned out of the question.
Okay, I don't know what happened. So I'm wondering, what's the time scale for a flux tube to rise to the surface? Can you give us an estimate? It's 1 hour, it's 1 day, in a few days, or in a few weeks, or in a few months?
Sorry, I do not actually have a handy number for that, but I look up how the non-dimensionalization has happened, and I'll get back to you with those numbers if I can actually arrive at them. They also depend on what the strength of the field is. So we also vary the strength of the flux tube. That changes the rise time. So I'll get back to you with the case which we studied most extensively and what the rise times were for that particular case when we convert them to dimensional units. I do not have an answer right away. Sorry.
Anybody else?
So try to answer your question on the chat. Hell and anti-hell. That suppose you have the perfect rotation and all the flux tube should be following the Hell law. That is the tilt angle is the one sign in one hemisphere and the other sign in the other hemisphere. But the simulation showing here basically look at the twist, but not the tilt angle. And the total helicity basically is a combination of the total of twist and the tilt angle, which is a proxy of the magnetic rise. When magnetic tube emerge, the helicity is conserved. Means when the flux tube emerge from a convection zone, the rotation clearly force action on the rising flux tube, and then generate magnetic rise, that tilt angle. And then the same helicity, but the opposite sign will be generated as a twist. So when simulation look at the twist, that for the ideal case, all the twist should be follow the hemisphere rule. But if the flux tube has an original twist, that would cause a difference or discrepancy from the hemisphere rule. Means some helicity, some twist just convert to the rise with the same sign. So those flux tube or active region might not follow the hemisphere rule. So the bottom line is where the original twist come from. This kind of things that's kind of involve also into the hemisphere rule.
Yeah, thanks, Yang. I mean, very interesting point, because you could have some flux tubes which have some initial twist and they might be rising, but because they are rising through the convection zone, they develop some right, and then it might try to sort of cancel out the initial twist that was, and maybe also create violations in this particular case. So yeah, that's possible. That's one way violations might occur in the real observations that we see.
Thanks. Well, we are a little over time, so let's thank the speaker again. Thank you very much. It was great. Congratulations, Dr. Manek. Yeah, well, I mean, people, I guess, are free to stick around and ask some more questions. I have to go to another meeting,
yes, let's thank to the speaker again, and the recording will be online soon at the normal place at the COFFIES website as usual. So see you next month.
See you. Bye-bye.
Thank you.